So when all the solar excitement from space weather that Tom talked about slams into the Earth, the first thing it hits is the upper atmosphere, and Stan's going to be telling us a little bit about that. He's an HAO senior scientist specializing in physics and chemistry of the Earth's upper atmosphere and ionosphere, degrees from Harvard and the University of Michigan, has a background as a postdoc visiting scientist here at NCAR. He joined LASP, where he became the interdisciplinary scientist for NASA's timed mission and the deputy PI and project manager for SNOWY. Then from 2005 to 2010, he was the deputy director or the acting director of HAO. And now he's going to be telling us about what he calls down to the upper atmosphere. When do the models arrive?
Thank you. I got to do this first. This is the shot. So we're going to talk about observations and models of the ionosphere, upper atmosphere of the Earth, and our efforts to use them together to improve both. But I want to start by trying to define terms. This is a question I got as a PA in grad school. What do you mean by a model? Well, a numerical digital model isn't really that different from a ship in a bottle. It's equally fanciful, mysterious in the way that it's assembled. But in this case, we're trying to represent reality with small numbers instead of with small parts. But language is important. I'm reminded of this because Jim Stone used to run a series of workshops at the NASA Huntsville Marshall Space Flight Center, and he would invite the solar wind people, Magnetosphere modelers, Ionosphere-lonosphere modelers to come down and apply their trade. One year, he had the meeting off-site in the nearby state park, and I flew in with Mike Wiltberger and John Ryan. And I flew in with John Ryan and Mike Wiltberger, and rented a car, drove out into the woods, try to find the state park and the lodge, getting a little bit of that deliverance skill. Finally, we got the lodge and checked in at the desk. Is it turned on?
Sorry, Stan.
How's that?
Keep talking.
Where are your collar?
Sorry, Stan. Yeah.
Or you can stand by the podium. The one Tom had was working fine. No, he was behind the podium. Cool. We'll go with the podium mic then. So what is a model? I just remember flying into the Huntsville modeling workshop and driving with John Lyon and Mike Wiltberger out to the state park. We checked in at the front desk. The guy immediately noticed, oh yeah, you guys are here for the Huntsville modeling workshop. And there were a couple other guys lurking behind the front desk, and we said, yeah, that's us. We're here for the Huntsville modeling workshop. And one of the guys would come up from the back and said, so you all the photographers? and Mike said, yeah, I guess so. And the other guy comes up and says, well, when do the models get here? and Mike said, well, tomorrow. But you might be disappointed. But anyway, okay, so we know why we're here, because, okay, you're about to get the 30-second version if you missed Tom Bogdan's talk last night. One word, molybdenum. 75 years ago today, Walt Roberts and Janet Roberts drove across the Great Plains with the Harvard College Observatory chronoscope in the back of their car. and deployed it at the Climax mine of the molybdenum mine of the Climax Mining Company at the Fremont Pass station, and proceeded to make a one-year graduate study so that Walt could finish his dissertation and get some measurements of the sun. It was a one-year assignment. So the real question is, why did they stay? And the reason is because the National Bureau of Standards thought that somehow the solar corona was connected to the ionosphere. And subsequently, during the war, the US Navy provided for additional funding to continue the operation. And subsequent to that, I think there was the idea that perhaps research and more measurements would give us insight, not just into the connective, the predictive aspects, but also into the mechanisms connecting the solar events to the ionosphere. So 75 years later, still trying to figure it out. And so we do understand the basics. As just reviewed, the sun has three main ways of influencing the upper atmosphere and the ionosphere of the Earth. First, fairly directly, extreme ultraviolet and X-rays all the time, but especially during flares, ionizing the thermosphere and creating the ionosphere. Energetic particles that are sometimes consequent to those flares are transported and sometimes accelerated by the heliosphere and then penetrate the atmosphere, actually to sometimes quite low altitudes. And thirdly, and most mysteriously, the solar wind and the interplanetary magnetic field of the extended solar atmosphere is transmitted through the heliosphere, arrives at the magnetosphere where it disrupts it, generates auroral currents, which flow down into the high latitude ionosphere, causing more ionization and more heating as the circuit closes through the ionosphere. So 1 year ago today, I was preparing a different talk, and I was trying to find a way to illustrate just how difficult this is. And the sun sent me a gift, which was the coronal mass ejection on September 10th, 2014. It was a HALO CME, meaning that it was directed at the Earth. And based on the observation of that coronal mass ejection, the Space Weather Prediction Center put a pulse-like inner boundary condition into Dushan-Yggdrasil's Enlil model. This is a solar wind model, which transmits that solar wind variability through the heliosphere and to the Earth and beyond. So based on that and other information, SWPC issued a forecast of an event arriving late in the day on September 12th, and a moderate geomagnetic storm, and then a major geomagnetic storm on September 13th. This is ambitious because they're trying to predict it 2 days in advance, not just 10 minutes in advance. So what really happened? This is just broad brush. This is the KP index. It's a broad magnetic index of variability in the magnetic field in the ionosphere. And on September 12th, there was a little precursor event, and then right on time, right as predicted, the disturbance arrived. Geomagnetic activity got very high, or fairly high, and then as we turned to September 13th and the sun set here in Boulder and the skies cleared, we got nothing. The storm just died out and we just went dead quiet. So the reason for that is that if we look at this plot of actual measurements upstream of the Earth from the ACE satellite, ACE spacecraft, the wind speed did as predicted, small precursor event, and then the big jump late in the day on the 12th, and then it stayed high. The density of the solar wind went through some major disruptions during the course of that event. But if we look at the magnetic field, the interplanetary magnetic field, the white line is the total magnetic field. And when the event starts, it jumps up, it goes through a very variable phase, and then it stayed high throughout the event. But this red trace is the north-south component of the interplanetary magnetic field, so-called BZ, the Z component of that field. And it's only when that component is southward, when BZ is negative, that you get strong coupling between the solar wind and the magnetosphere. And what happened instead is it went variable for a while late on the 12th, and then it went north, and it stayed north through the whole event. And that's why we didn't get much. So the illustration here is why it's so difficult to predict that type of storm well in advance, is because it's so difficult to predict the interplanetary magnetic field. The reason it's so difficult to predict the interplanetary magnetic field, even though you have a good solar wind model, is that it's a slave to its inner boundary condition. So the interface between the corona and the heliosphere is key. You have to understand the magnetic field there if you want to have any hope of propagating it to the Earth. But we do have measurements, such as these, upstream of the Earth, and ultimately we will have predictions of the interplanetary magnetic field of the Earth, and when we do, we will be ready for them because we have powerful models, such as the coupled Magnetosphere-Ionosphere-Thermosphere model. A CME arrives upstream of the magnetosphere, distorts and extends the magnetic field. You get reconnection deep in the tail. Auroral currents flow down into the polar regions, ionizing them and creating joule heating from the closing of the currents. And this stirs up the polar ionosphere. Here we have the increases in electron density and the ion drifts as they're pushed by the magnetosphere through the atmosphere. That causes heating, the neutral temperature, and entrains the neutral wind system. The way we describe this is with Ray Robles' model, or one of Ray Robles' models. This is the Thermosphere-lonosphere-Electrodynamics general circulation model, the TIE-GCM, developed by Ray with collaborators, Bob Dickinson, Art Richmond, and now much of the AIM section here at the Atmosphere, Ionosphere, Magnetosphere section here at HAO. When we couple it to the Lyon-Fetter-Mowbray magnetosphere model, we call it CMIT, the coupled Magnetosphere-Ionosphere-Thermosphere model. And this is work that's been being carried out by Mike Wilberger, Wenbin Wang, others in the section. It's a community model. It's open source. Code's available. Version 2 release, the high resolution version, is imminent. We have manuals, we have documentation, and you can run it on the web at the NASA Community Coordinated Modeling Center. More information here. What I'd like to do is just illustrate that according to this model and some of our measurements, the effect of these geomagnetic storms in the ionosphere and thermosphere are not confined to the polar regions, but are global in extent. This is the geostationary view, as if you were on say, a communication satellite at geostationary orbit. There's a lot going on here. This is the E region. This is where you can see the aurora. So when the big storm hits, the aurora blossoms. When it does, it heats the polar thermosphere, but then a big wave, I'll wait for one more iteration here, this is just looping. A big wave of temperature variation spreads out across the whole globe. That disrupts the composition of the thermosphere, the atomic to molecular composition ratio changes, and all of these things, the electric field, the heating, and the changes in atmospheric composition affect the upper ionosphere, the so-called F region, the high altitude ionosphere, which has a lot to do with communications and navigation disruptions. So, in fact, we do have a fairly detailed model-based understanding of how the ionosphere responds to these events far away in the corona. However, all of this is played out against a backdrop of extreme variability in the solar cycle, here illustrated in the EUV radiation as it goes from solar minimum to solar maximum. There's both more structure, but also more of it at solar maximum. And this puts a big change into the thermospheric temperature and an order of magnitude change into thermospheric densities at high altitude. This is at 400 kilometer. This is a very broad brush way. It's almost the climate of the thermosphere goes through the cycles, and what we're doing is comparing a measurement derived from satellite drag observations by John Emmert. He uses thousands of objects in orbit to map the time history of the global mean thermospheric density, and then we sample the model in a similar way, very broad brush, and when you do that, you can see these storms. Especially the big ones, for some reason they come on minor holidays, and so they have names: Bastille Day, Halloween, St. Patrick's Day. But they're not the most obvious thing on this plot. I mean, the big thing you see here is this order of magnitude, log scale, order of magnitude variation in density with a solar cycle. And then there's this structure, which as you get to solar minimum, you start to see a pattern in it. It's a very strong annual and semi-annual variation of the density. And you see that in the ionosphere as well. And then another thing I'll point out about this plot is that when you get to solar minimum, you know, the model's doing pretty well. It's tracking the gross features. It's capturing these storms, for better or for worse. It's getting this seasonal variation, largely because we sort of put it in there by brute force. But then at solar minimum, there's some variability in the density that's just not captured by the model. The model thinks everything's quiet, but the measurement knows that there's more going on. And the reason, or one of the reasons, is that when I showed you this plot, I left off a very important piece deliberately, which is that we now have a firmer understanding that the lower atmosphere, the middle atmosphere, has a lot to do with controlling this realm. And that's through the large-scale motions of tides and planetary waves. It's through the small-scale turbulence and convective motions, and also other ways to couple into the thermosphere-ionosphere system. So in order to understand this in its entirety, you have to take it to the next level. And that level will be the whole atmosphere community climate model, X. X is for extended. These are meridional winds, a very high resolution simulation done by Han-Li Liu, showing the variable wave structure propagating all the way up from the troposphere. And our current efforts are geared towards putting an ionosphere into WACOM-X. Han-Li will talk about this tomorrow in much more detail. I just want to show you these fish swimming across the globe. This is the equatorial F region of the ionosphere with somewhat more structure and somewhat more complexity as now modeled by WACOM-X. We would like for this model to become a space weather model. It's going to take a lot more work. I also want to point out that the second big C stands for climate, which is one of our fundamental goals in trying to extend this work, to try to understand the climate system of the Earth in its entirety. There's another way that the lower atmosphere couples into the upper atmosphere, and that was predicted by Ray Roble, Bob Dickinson, in 1989, and which is that as carbon dioxide and other greenhouse gases build up in the lower atmosphere, they diffuse up into the upper atmosphere. And although these greenhouse gases are called that because they heat the lower atmosphere by trapping radiation, as the atmosphere becomes optically thin at higher altitude, they emit radiation, thereby cooling the upper atmosphere. So Roble's prediction, Roble and Dickinson's prediction, was that if you double CO2, as eventually it will, the neutral temperature in the thermosphere will reduce by 50 degrees or more. This is the largest global change observable in the atmosphere. And when you cool the temperature, you reduce the density, and you are predicted to see very large, maybe half, a factor of 2 decrease in thermospheric densities, and that's measurable because we have all those satellite drag measurements. So this was another case of the theory preceding observation, but people went out to try to look for this, and they found it. First, Jerry Keating looked at satellite drag data, that topic again, from one solar minimum to the next, and you can observe that there's about a 5% per decade decrease in thermospheric density at solar minimum. These data are John Emmert's data. Keating did it with just a few objects and only at solar minimum because he had to take out this huge solar cycle signal, which complicates things entirely. Emmert attempts to remove that with a combination of modeling and removing the secular from the cyclical terms with statistics. This is just the solar cycle, commonly used index. And then other researchers, Frank Marcos, and now in the UK, have confirmed this result. So it's a very firm result. There's definitely a systematic decrease in thermospheric density as predicted. So just when we thought we had a handle on this, things got more interesting. We thought we were at solar minimum in 2007, and then in 2008 and 2009, this happened. The thermosphere went to 30% lower than it had previously been observed. And this presents somewhat of a conundrum for people interested in thermospheric climate, but also for modelers. Now, I showed you this plot a minute ago, and claimed that we're doing pretty good on this broad brush level in terms of understanding thermospheric climate. What I didn't point out is that we also get the 30% low, whoops. We also get the 30% lower effect. And that's because there's a lot of controversy about exactly what the solar EUV radiation levels were doing. The ones we use, which are based on magnesium-2 and Lyman alpha and some measurements, show that the main cause of this 30% decrease was lower solar EUV radiation, but also that the decrease in magnetic activity, which heats the thermosphere, which is also lower during this solar minimum, was important, and of course the ongoing increase in CO2 also helped decrease the thermosphere. So this is an area of active controversy and research trying to sort out these factors and possibly other factors. One hope for being able to do this better in the future is better measurements, especially space-based measurements. We're now building over at LASP the Global Observations of the Lemon Disk instrument, which will fly on a commercial communication satellite at geostationary orbit and obtain global measurements of composition and temperature, at least that much of the globe that you can see during the daytime. And then the Ionosphere Connections Explorer being built out at Berkeley will largely equatorial orbit will make measurements of the dynamics of the equatorial ionosphere and some of the disturbances in it that are very important for communications and navigation. And while that's going on, we have been the great good fortune to benefit from these constellation missions that were not designed with the ionosphere in mind, but have to cope with the ionosphere and the thermosphere nonetheless. COSMIC is primarily a troposphere mission, but it makes very important ionosphere measurements, and COSMIC 2 will have a whole lot more cosmic satellites, which will be a wonderful thing for ionospheric science. SWARM measures thermospheric densities and velocities in addition to the magnetic field, and then this Ampere project exploits magnetometers on the Iridium telecommunications constellation, from which you can infer auroral currents, which, as I showed, are very important for understanding the geomagnetic forcing of the thermosphere and ionosphere. Just as a preview of things to come, this is some magnificent work by Jinan Yue over at the COSMIC program. He has essentially a data assimilation model. It's called a reanalysis product, combining measurements from COSMIC and other GPS satellites in orbit with ground-based GPS and then using an empirical model to improve those measurements so that we have a coherent representation of the ionosphere during quiet times and storm times. And here he compares them with predictions from the TIE-GCM. It's not perfect. We do capture some of the main features and the changes. The color scale has changed subtly in these displays, so it looks a little better than it really is. But it really points us in the direction of what we have to do to improve the model and improve its fidelity and also improve its performance. Now, everybody understands the ionosphere is important. I think today we understand more about why the thermosphere is important. One of the reasons is that the upper thermosphere, which I explained was mostly atomic oxygen, is now being populated by aluminum, titanium, molybdenum, and especially at low Earth orbit. Things are getting very crowded, and at low Earth orbit, this is the region where the neutral atmosphere changes trajectories and means that collisions can occur if we're not careful with space navigation, sometimes collisions with unintended consequences. So in the next talk, Dolores Knipp will discuss this and related matters. I'll leave you with that, and thank you very much for your attention.
Questions for Stan? He's given himself time for a lot of good interactions. Yes, Alice.
Thank you, Stan, for a wonderful talk. I just have a couple questions. One of which is you mentioned knowing the direction of the magnetic field. So two-part question. That's the first one, is knowing what that direction is, and do we have better instrumentation to look at that? And then you showed a whole bunch of satellites looking at the ionosphere, thermosphere, looking down on the Earth. Are there other instruments that we might be able to build looking up that would be very helpful?
There's a whole host of observatories from the ground that using incoherent scatter radar, Fabry-Perot interferometry, and now electron content from GPS observations they're very important in this. The reason that Shannon is able to get that global coverage is you have global coverage from the satellites, but it's sparse, and you have much greater density of coverage from ground-based, but it's erratic because you don't have that many stations over the ocean. So it's a combination of ground-based and space-based data that'll be most powerful. Circling back to your first point, I mean we have the upstream measurements of solar wind and interplanetary magnetic field, and that gives us half an hour or more lead time to be able to make magnetosphere-ionosphere forecasts, and that's very important. What I was alluding to, or maybe suggesting, or maybe precursoring tomorrow's presentations, is that the promise of coronal observations may be that if we can say something a little more quantitative about the actual magnetic field consequent to coronal events, that we might be able to get better predictability in solar wind models and hence geomagnetic models.
Sam, where do you see the models going in terms of going down, in terms of what's needed to improve the models, the coupling to the lower atmosphere, and where do you see the future going there?
Well, clearly our future is towards whole atmosphere modeling. This is the thrust of what we're trying to accomplish in this section. It's the thrust of many of the strategic goals of NCAR. I think it's compelling both from an intellectual standpoint, whether or not you think that the mesosphere or the thermosphere is important to your climate model. It's important to people who care about the mesosphere and thermosphere, and it forces us to take an integrated view of the entire atmosphere as it goes through these vast changes from a radiationally trapped region to a radiationally emitting region, from a turbulent region to a diffusive region. And the challenge is that it turns out to be incredibly hard. Putting actual thermospheric and ionospheric observations on top of a model that's been tuned to try to get the mesospheric jets right, which is also incredibly hard, is an unbelievably daunting task. So for some problems, if what you really care about is the effect of a big auroral storm on the upper ionosphere, you don't necessarily have to go to the completely complicated approach of understanding every little bit of the troposphere. And conversely, if what you want us to understand is the propagation of stratospheric warmings into the lower ionosphere, well, maybe you don't have to consider space weather while you're looking at that problem in isolation. The ultimate goal is to bring that all together and perhaps someday have that proverbial sun to mud model. Right now I say sun to mud, yeah, that's right, sun to mesosphere under development.
Well, thanks, Stan. Oh, one more, Phil.
Thank you. This is a discussion we've had at HAO from time to time, and I just want to bring up in front of this group a question that strikes me as being an important one to ask, and that is, from the point of view of fundamental physics, we have no clear idea what the input or the dissipation mechanisms of energy are in the corona, and yet this thing is helping to drive a lot of the ionosphere. By contrast, the ionosphere-thermosphere, it seems to me as if the success of the models now suggests you should be moving to an operational mode. In other words, there's no fundamental questions anymore in the ionosphere. And so I'm wondering if you believe that's the case. If not, please tell me what the fundamental questions are, because from the point of view of fundamental physics, I can't see them anymore.
Probably the biggest challenge is understanding the transition from a turbulent regime to a diffusive regime. And the word subgrid scale appears in it appears in both the solar interior modeling and in the meteorological modeling talks that we've heard already. But it's not really, subgrid scale just means that our computers can't go there yet. There is something mysterious going on in the lower thermosphere in this transition region from turbulent to diffusion that interferes with our ability to understand the composition and consequently the ionosphere. The other fundamental issues have to do with acceleration of auroral particles, which we tend to take as a given, as an empirical fact, but are still somewhat mysterious as they occur in the lower magnetosphere, and the nature and details of how ion-neutral interactions occur. All those things notwithstanding, we should be able to construct meaningful numerical models just as meteorologists can construct meaningful weather models without having to know every single detail about cloud formation or precipitation generation. And consequently, as we move toward a functional representation, we are compelled to think about the operational goals. I don't think that you don't want to oversell this because operations has to move very slowly into these theoretical and numerical realms, but it has to be one of the goals because do I got to quote Walt here? Science in the service of society.
Okay, let's again, thanks Dan again.